Hello friends, here in this video we are going to see a problem which is based on Otto cycle. Here is the question. Now in this question, whatever is mentioned we are going to write that in the form of data by reading the question. So the first step would be to write the data. Now I will start reading the question. A certain quantity of air at a pressure of 1 bar and temperature of 70 degrees Celsius. So initial pressure and initial temperature of air is given. That initial pressure is P1 is equal to 1 bar, which is 10 raised to 5 Newton per meter square, and the initial temperature is 70 degrees Celsius given. So it is T1 is equal to 70 degrees Celsius. Now in this, if we add 273, the temperature T1 will be in terms of Kelvin, which is 343 Kelvin. Next is compressed adiabatically until the pressure is 7 bar, means the air which was at initial pressure of 1 bar, now after compressing it adiabatically, the pressure has become 7 bar. It means this is pressure value P2. So after P1, P2 is equal to 7 bar, which is 7 into 10 raised to 5 Newton per meter square. So 7 bar in Otto cycle engine. So here the type is given, so I'll write the type. In this case it is Otto cycle. Now 465 kilojoule of heat per kg of air is now added at constant volume. In case of Otto cycle, the heat gets added at constant volume and that heat is given as 465 kilojoule, and since it is on per kg basis, so I'll write down, therefore heat added Q suffix A, it is called as the amount of heat added, and it is 465 kilojoule per kg. So from this it is clear that here we have to take mass of air as 1 kg. Now determine, there are 3 questions which have been asked here. First is compression ratio of the engine. Compression ratio is denoted by R suffix C. Next, temperature at the end of compression. So temperature at the end of compression will be T2, and then temperature at the end of heat addition. Heat addition gets started at point number 2 and it gets completed at point 3. So temperature at the end of heat addition means we have to calculate T3, and accordingly these terms would be understood once I start the solution. That is, in the solution part I will be drawing the PV and TS diagram. From that we can get an idea that what temperatures are to be calculated. Next, take for air, some values are given for air. Cp, that is specific heat at constant pressure, is 1 kilojoule per kg Kelvin. So Cp is equal to, we have to take for air 1 kilojoule per kg Kelvin, and Cv, specific heat at constant volume, that is 0.706 kilojoule per kg Kelvin. Now with the data available to us and we have understood what are the unknowns to be calculated, let us try to get the solution to this problem. Now in the solution part, since it is given that here the type of cycle is Otto, so for Otto cycle we need to draw PV and TS diagram. So I'll write down that first I am drawing PV, that is pressure volume, and TS, that is temperature entropy diagram for Otto cycle, and that diagram now I am going to draw. now in the PV and TS diagram, first I'll start with PV diagram. In case of Otto cycle, there are 4 processes. Process 1 is called as adiabatic compression, and that adiabatic compression can be shown on PV diagram with the help of a curve. Here this curve, it indicates process 1 to 2, which is adiabatic compression. Now in case of adiabatic compression, as it is clear from the diagram, at point 1 the volume is V1, at point 2 the volume is V2. So from V1 to V2 the volume has decreased, but pressure increases from point 1, that is P1, up to P2. So we have understood that during the adiabatic compression process, volume decreases, pressure increases. Next, since Otto cycle is also called as constant volume cycle, the heat will be added at constant volume. So here from point 2 the heat addition will start, and it will be added at constant volume up to point number 3. So this is the constant volume heat addition. So I can say volume at 2 is equal to volume at point 3. After this, there is expansion from point 3 to point 4, and again the expansion, like compression, it was adiabatic, or we can say isentropic. Similarly, the expansion process is also reversible adiabatic, or we can say isentropic process from 3 to 4. Next, process 4 to 1 is heat rejection at constant volume. So here we can say that V1 is equal to V4. Now during the compression and expansion process, both, the law followed is PV raised to gamma is equal to constant. This law is for reversible adiabatic or isentropic process. Since the compression and expansion, they take place as reversible adiabatic process, so it follows the law PV raised to gamma is equal to constant. Next, during process 2 to 3, the heat is added, so I'll write down Q suffix A. Next, during process 4 to 1, the heat is rejected, so that is Q suffix R. Now once I have drawn the PV diagram, next thing would be to draw the TS diagram. And in this TS diagram, the first process is isentropic compression. So during process 1 to 2, entropy will remain constant, and during compression process the temperature rises. So as I can see in the diagram here, S1 is equal to S2, that is the entropy remains constant. Next, after that heat is added at constant volume. So here I am drawing a constant volume line. Now over this constant volume line, since heat is added at constant volume, so from point 2 to point 3 the process will follow this constant volume line. Here I am getting point 3, and since the heat is added, temperature at point 3 is greater than the temperature at point 2. So now here, as we are drawing the PV and TS diagram for constant volume cycle, that is Otto cycle, process 2 to 3 is constant volume heat addition, 3 to 4 was again isentropic expansion. So 3 to 4 will be isentropic expansion, that is entropy will remain constant. So I'll write down S3 is equal to S4. Entropy is constant, but as we see there is drop in temperature from point 3 to point 4. So this drop in temperature is utilized to develop some work, and that work is called as work which we would be getting in the expansion process. Next, after we have attained the expansion, then there is heat rejection which is at constant volume, and for that heat rejection again I'll draw a constant volume line. and since heat is rejected from point 4 to 1, so heat will be rejected here from point 4 to 1, and again it follows a constant volume line, that is volume of point 1 and point 4 they are same as previously, volume of 2 and 3 they were same. Now during 1 to 2 the work is done during compression, or we can say the work is done on the air during compression process. Next, from 2 to 3 the heat has been added, so this will become QA. For process 3 to 4 there is work which we are getting in expansion process, and 4 to 1 is the heat which is rejected out of the system. So similarly I can mark here on the PV diagram that during 1 to 2 the work is done in compression, and from 3 to 4 the work we are getting in expansion. Now once we have drawn the PV and TS diagram, I can explain it again, that what we have to calculate here. The first thing is compression ratio of the engine, which is denoted as R suffix C. Next is temperature at the end of compression. So if we see, compression starts from point number 1 and it gets completed at point number 2. So temperature at the end of compression means we have to find out the value of T2. So as I have written in the data, we have to find out T2 as the second question. And then the third question is temperature at the end of heat addition. Now we see that heat addition at constant volume, it starts at point number 2 and finishes at point number 3. So temperature at the end of heat addition means we have to calculate the value of T3. So here we have understood that how many unknowns are there and what we have to calculate from them. So first I'll start with the calculation of RC, which is called as compression ratio. So it is calculation of compression ratio. Now I'll write down that since for process 1 to 2, which is also called as isentropic process, here the relation can be written as T2 upon T1, that is higher temperature upon lower temperature, is equal to V1 by V2 raised to gamma minus 1, and this is also equal to P2 by P1 raised to gamma minus 1 upon gamma. This is the relation of isentropic process, and after writing this relation, this was the relation between temperature, volume and pressure. Now I'll write one more relation which is related to PV raised to gamma is equal to constant for state 1 and 2. I'll write down that after this, therefore P1 V1 raised to gamma is equal to P2 V2 raised to gamma. This we are writing since the process is reversible isentropic process. So now I'll utilize this relation. So therefore here I'll write it in a special form, that is P2, I'll shift P1 here, so it will be, here we are left with V1 raised to gamma, and V2 raised to gamma I'll bring it onto the left hand side. Here we have P2, this P1 will go into the denominator. So after this, therefore V1 by V2, this gamma I can take it as common, so it is common raised to power gamma, equal to P2 by P1. Now P2 by P1, if I see in the data, P2 and P1 values are given, that is P2 is equal to 7 bar, P1 is equal to 1 bar. So 7 into 10 raised to 5, I am writing it in terms of Newton per meter square. Again, P1 is 1 into 10 raised to 5 Newton per meter square. 10 raised to 5, 10 raised to 5 will get cancelled out. So it means if we are writing the pressure ratio, then we can directly write it in terms of bar, because in terms of Newton per meter square it will get cancelled out. Next, therefore, V1 by V2 is nothing but it is called as compression ratio RC is equal to, now here we have 7 upon 1, which is 7 raised to the power. Now this gamma, when it goes onto the other side, it would become 1 upon gamma. Now after writing this, I'll say that where R suffix C, it is called as compression ratio and it is equal to cylinder volume upon clearance volume. So therefore RC can be written as, now from the PV diagram it is clear that V1 is the volume of the cylinder volume. So V1, clearance volume is only up to 0.2, so V2 is the clearance volume. So V1 by V2 is RC. Now this gamma value we don't have. It is not given in the data, but Cp and Cv values are given. So I'll be keeping this as equation number 1 and I'll go for the calculation of gamma. So after reaching this stage, I'll say that therefore gamma, it is called as adiabatic index. So adiabatic index gamma is equal to Cp upon Cv, that is the relation of gamma. Cp is specific heat at constant volume, constant pressure. Cv is specific heat at constant volume. So therefore gamma will become, now Cp is given, it is 1 kilojoule per kg Kelvin. Cv 0.706. So therefore gamma value, it comes out to be 1.41. Now after getting this gamma value, I will put it in equation number 1, wherein we will be getting the value of RC. So I'll write down, therefore put gamma is equal to 1.41 in equation number 1. So now here I am putting gamma is equal to 1.41 in equation number 1. Therefore in equation 1 we had R suffix T is equal to 7 raised to the power 1 upon gamma. So that will be R suffix C is equal to 7 raised to the power, now 1 upon gamma, gamma is 1.41. So from this I'll get the value of RC on the calculation and my answer is 3.975. So here is the first answer, that is we have calculated the value of compression ratio. Now after the compression ratio, the next question was to get the value of T2, that is the temperature after compression. So here I'll write down calculation of temperature at the end of compression process. Now temperature at the end of compression process, since we know that the compression is at isotropic, or we can say reversible adiabatic, and for reversible adiabatic compression we can use this relation, that is previously which I have written for process 1 to 2. Now T2 by T1 can be written as V1 by V2 raised to gamma minus 1. So therefore T2 by T1 is equal to V1 by V2 raised to gamma minus 1. and this relation is for since the process is reversible, adiabatic or isentropic process. Now after writing this relation, I'll say that therefore T2 by T1 is equal to V1 by V2 is nothing, it is called as RC, that is compression ratio, and that compression ratio value is, we have found out it was 3.975, that was our first answer, raised to gamma, which was 1.41 minus 1. So therefore here I'll get it as T2 by T1 is equal to, this complete value is 1.76. so T2, this T1 I'll send on to the other side, and the value of T1 is 343. So 343 will be multiplied here, that is 1.76 into 343, and hence the answer T2 comes out to be 603.68 Kelvin. So this is the temperature at the end of compression process, and our answer number second. After reaching here, the last question was to calculate the temperature at the end of heat addition, which is T3. So calculation of temperature at the end of heat addition process. So now to calculate the temperature at the end of heat addition process, I will utilize the heat added which is given in the problem. I'll say that since for constant volume heat addition for Otto cycle, I can write down QA, that is heat added at constant volume, is equal to mCV into T3 minus T2. This can be explained from the it is PV and TS diagram. Here heat is added at constant volume from point 2 to point 3. So this heat added can be written as mCV because it is at constant volume into temperature difference T3 minus T2. So mCV T3 minus T2. Now therefore this heat addition is given in the problem, and that value is 465 kilojoule per kg, mass is 1 kg, CV value 0.706 given, into T3 minus T2 we have found out, it was our second answer, and it was 603.68. So therefore here on calculation of this entire term, I'll get my answer of T3 as 1262.32 Kelvin. This will be the third answer. And if we look into the question, as per the three unknown values, the first one was RC. We have found out RC value was it came out to be 3.975, that was the first answer. Next, T2 temperature at the end of compression, it was found to be 603.68 Kelvin, second answer. And the third part was T3, the answer is 1262.32 Kelvin, and we have found out T3, and with this we complete the question.